Good morning. So let's continue with our discussion on thermal conduction, and I want to bring about one practical application where the principles that we have used so far can be easily applied. And the motivation for this thing that I'm going to talk about is something like this. So say that you have a plain wall. Okay, we looked at a plain wall so far, and there is no heat generation. And say that we have some the wall is exposed to some fluid on one end and maybe another fluid on the other end, and say that T infinity 1 is more than T infinity 2. So let's say that heat goes from left to right, so we have heat transfer taking place in that direction where I can define X, something like that. Okay, now it is that the principles that we use, you can actually calculate Qx at steady state using the data that is given, of course, knowing that the thermal conductivity of the material is K, its thickness is L, let's say. Now let's say I want to make sure that I want to reduce the amount of heat, so I want to create a situation where I don't want energy exchange to happen between the inner and the outer fluid. So one of the things that I can do is I can add some insulation. So for instance, I can add maybe an insulating layer on one end. So this is an insulator. An insulator is something which has a very low thermal conductivity. So say the insulator is made of material B and this is material A. So as long as KB is much less than Ka, what do you think should happen to Qx? So I hope you all agree that Qx will decrease. It's the same potential, it's the same difference in thermal potential, which is T infinity 1 and T infinity 2. So T infinity 1 minus T infinity 2 is the same, but adding in insulation is actually going to create more conduction resistance. So the heat current will actually decrease. So that is quite easily understood in the case of plain slab. But this doesn't work out the same way in the case of a cylindrical shell or a spherical pipe. And I want to discuss that today, that why adding insulation may not be beneficial. It is beneficial if you only go beyond a certain number. So if you consider let's say a cylindrical shell, say we have some fluid inside in the core of the cylinder. We have, say, the solid extending from some distance r1 to r2. So this is actually the solid part. That donut is where the solid cylinder actually exists. Okay, internally maybe there is some fluid. Sorry, I'm not very concerned about that right now, but there is, let's say, some temperature on the internal surface, which is T1. And let's say I want to add some insulation to this donut, okay, or to this pipe which is going into the plane of the paper. So let's add an insulation. So we have, let's say, an insulating layer which might be of, let's say, this type. So the outer radius, I should say, of this layer is, let's say, uh, yeah, let's say R3. Okay. Now, say that the cylinder is the cylinder is actually exposed to a fluid which has a heat transfer coefficient of H, temperature T infinity. So, from a thermal circuit perspective, right, what I can say is, so we have a conduction resistance, let's say from T1 and to some temperature, maybe T2 on the solid. So T1 goes to T2, then there's resistance from the insulation, which is, let's say, R conduction maybe 1. I can say R conduction 2, and then we have a convection resistance to T infinity. So this is T1, T2, I don't know, some T3 which we don't know, and T infinity. So T3 would be somewhere here. So we have the conduction resistance, the inner conduction resistance, which I can say is, let's say, log R2 by R1 by 2 pi L K of the material, let's say K, I don't know, K of the tube or the cylinder. Then we have log of R3 by R2 by 2 pi L, let's say K of the insulator, which I've added as insulation. And then we have 1 by H A3 as a convection resistance on the outer surface of the insulation. Now, the point that I'm trying to now reach to is that, as I was saying, that in the case of a plain slab, you get an increase in resistance when you add an insulation, and that happens primarily because the area of the insulation is the same as the area of the slab. In a radial system, such as I said, a sphere or a cylinder, the same, this is not true for the insulation, or whatever you add on the outer periphery, because the area is actually increasing as you go out. So you can see that even though by adding an insulation, which is this part, the conduction resistance is actually increased. Okay, because log R3 is actually going to go higher. You are adding, so we are trying to see what should be the radius, outer radius of this insulation, what should be a good number for that. So this number, even though this will increase, log R3 will increase, but I can also see that A3, which is inversely proportional to R3, will actually be also increasing. So this number, the convection resistance, will actually decrease. So the conduction resistance increases, convection resistance decreases. It so happens that when you add look at the interplay between these two numbers, log of R3 and 1 by R3, actually initially R3 grows, or R3, I should say 1 by R3 decreases faster as compared to how log R3 increases. But at some point, log R3 will take over, and then by R3 will actually not decrease at the same rate as the rate at which log R3 increases. So you will have a decrease, or rather, an increase in overall resistance. So R, what I'm saying is R total in this case initially increases, or rather decreases, which implies that QR that we are trying to calculate will actually be increasing initially, but subsequently, beyond a critical number, this will actually decrease, or this will increase, and so QR will decrease. So we are interested in calculating what should be that critical number for this radius R3 at which this transition happens, when it goes from increasing, let's say, increasing heat transfer rate to a decrease in heat transfer rate. So it's very clear that I can write again, use the same electrical circuit analogy, and we can say that the heat transfer rate would be T1 minus, let's say, T3, T infinity, divided by a sum, the total resistance. But now I know that what I want to do is actually look at the point when R total is minimized, because R total being minimized will mean that I would have the point at which the transition from increasing heat transfer to decreasing heat transfer will actually happen. So I'm going to minimize R total with respect to R3, because that is something that I can control. I can control the amount of insulation I have to add on a particular, let's say, tube. So what we can do is we can look at R total, which happen to be these sum of these three constant, or these three numbers. So log of R2 by R1 by 2 pi L, let's say, KT, plus log of R3 by R2 by 2 pi L. And I'm going to drop the subscript I now, because I'm saying this is, it's understood that this is supposed to be the thermal conductivity of the insulator that we're adding, plus 1 by h 2 pi r3l. So to minimize with respect to r3, I need to take a derivative of this resistance with respect to r3. So that will give me a 1 by 2 pi lk r3 minus 1 by h2 pi r3 square l. And this, for the resistance to be minimum, should be 0. And so we can cancel out some common terms, which I am not doing here, just to keep it a little clean on this piece of paper. So what we'll have is, we can now prove that r3 would actually be equal to k by h. And let me say this is r critical. Why even say now r3? So this is r critical. So the critical radius of insulation in the case of a cylindrical problem, in the case of cylindrical conduction with insulation, is given by k by h. So you can prove, you can take the second derivative and prove that this will indeed be minimum, or rather, this our total would actually indeed become maximum at this, or rather minimum at this point. So you should verify that. I'm not doing this here. Take the second derivative and just put in this value and see. But what I can do is, qualitatively, if you plot the heat transfer rate versus, let's say, R3, if you plot this number or this variation, so we can go maybe from, so remember R3 can, the minimum value of R3 would actually be equal to R2, because that is the outer layer, the surface of the cylinder. So we'll start at some value of R2 and maybe go higher than that. So at R2, there is some amount of heat transfer. So initially the heat transfer rate increases until it reaches a maximum, and then it starts to decrease. So this maximum point where the heat transfer rate is highest is what is the critical radius. Now let me show you how this is important. It works in some, it becomes important especially when, in some scenarios, but in many cases it may not be even important. It is important especially when you have these current carrying conductors, when you add insulation on it, so the insulation has to have a certain uh, thickness. So these kinds of analysis actually help even in design of deciding on what is the layer of insulation on a particular conductor. But let me take an easier example. Let me take an example of a hot water pipe. So in a hot water pipe, you have the metallic shell. You have the cylinder, which is some kind of metallic layer, typically a stainless steel layer. But the insulation that you would add would typically have a conductivity which is much lower as compared to the conductivity of steel. So typical value that I can choose for a insulation is about 0.05, let's say, watt per meter Kelvin. And since it's flow of water in the tube, or rather, sorry, it's basically, if you're looking at not flow of water, but rather, let's say it's a surrounding air that is good, that can cool this water, right? This water layer. So there can be heat leakage from the hot water uh, pipe to the surrounding air. So typical value for heat transfer coefficient that I can choose, the maybe the on the higher end would be about 50 watt per meter square Kelvin. So let's say, just to choose some values. So in this case, the critical radius of insulation will come out to be about 10 raised to minus 3 meters, which is 1 millimeters. Now it's a very small number, and typically our pipes are much thicker. So we are way beyond this. So we are way beyond this critical radius. So so as an engineer, when you're deciding on the field, when you say that what should be the thickness of the insulation, you are actually pretty much on the right side of this number here. I hope you see this, that you're way far down here. So of course, you won't make a bad decision or a bad judgment by saying that maybe choose a 5 millimeter layer, a thickness which is about 5 millimeters, which is much larger as compared to the radius, which is 1 millimeter. So we can be at least confident that in such cases, the as an engineer, you will not be making a mistake, of choosing a layer which may seem to be, you know lower or inexcessive as compared to what is actually required. So you are going to be always on the right hand side. Things become tricky. Now this is also true, you should look at the case of when I'm sure you all have seen, installation of split air conditioners. So you know that they also have these tubings which are insulated with some foam. So please go and check, see what kind of heat transfer coefficients. When anyway, we'll do that in the later part of this course, but you should, if you're interested, look at what could be the heat transfer coefficient from the outer surface, and uh, what is the conductivity of that thermal foam. And let me also say that some of these, by the way, forgot to mention this, and yesterday I realized during the quiz. I would strongly recommend that you have the book with you at all times in all evaluations, because so far I'm giving you data, but at some point, you would have to look up your own data, and data is easily available on the back of this book. There are, in the book by Inkruper and Duvet, there is an entire layer or an entire array of these appendices where a lot of thermophysical data is given. So as an engineer, when I assign you a problem, I may say that, let's say you're working with steel. So I would not be giving you the thermal conductivity. You would need to check it on your own for a given temperature. So please start looking at that information again. Some of the later sheets now will actually be less direct. They may just give you some scenario, and you'll have to look up your own data. So keep that in mind. Okay, so this is just to complete our discussion on heat conduction without or steady state heat conduction with no heat generation. So let me now begin with heat conduction or steady state heat conduction with thermal generation or with heat generation. And we will consider situations in which heat is basically generated because there is energy conversion from one form to another. So the simplest example is one of the things that I gave in the quiz yesterday, that was ohmic heating. So you have a current carrying conductor, so you have I square r, amount of heat that is generated. We can have nuclear reaction if you're dealing with nuclear reactions, especially nuclear rods. So because in a nuclear reactor you slow down the neutrons, so slowing down these high kinetic energy neutrons causes them to dissipate that amount of kinetic energy as heat. So you can have heating in a nuclear reactor. You can also have some kind of chemical reaction, either an exothermic or an endothermic reaction. So it need not mean that heat is generated. Thermal generation means, in general, it could be, a positive heat release, or a negative, or a heat consumption, heat dissipation, or heat consumption. So keep that in mind, that it need not be always positive. We can also have, so as I was saying, you can also have an endothermic reaction where heat is actually being consumed by the reaction itself. So I'll start again with the simplest possible case, which is of the plane wall. So say that we have a plane wall which has, uh, which is exposed to a fluid on one end again, H1 and T infinity 1. Okay, so I was just saying we have a plane slab, let's say, which is exposed to two fluids on either ends. This time Q dot is not zero, so we have heat generation, but we're still looking at a steady state problem. Let's say that the thermal conductivity of the medium is constant, to keep the analysis a little simple. And what I do in these kind of problems, what is typically done geometrically is, so we divide the problem into two parts, or rather we divide the geometry into two subparts by taking the center line approach. So basically what we can do is, in these kinds of problems, we define the coordinate system to be based on the center line of the slab. So we can say x0 is here, and we say that the geometry is such that the slab thickness is 2L. Okay, so the coordinate is defined based on some x from here, and there's a reason for it. I'll show you what is a specific reason why we end up doing this. Because any geometry can be written as, it can be defined in terms of two times a number, a two times a length scale. So in this case, depending on many different factors, we will have a temperature distribution at steady state which would look something like this. And I'll prove that today, why the temperature distribution comes out of that type. So we'll have some distribution which will have maybe TS1 on one side, and maybe TS2 on the other side. These temperatures will be constant because we are working at steady state, so temperatures should not change with time, but their values we will see how to determine them eventually. Now there are two ways of solving this problem, and I'll quickly look at both. One way is the traditional way, which is using the heat diffusion equation. So I say that k is constant, we can write that d to t dx square plus q dot by k is 0. So that would basically be the heat diffusion equation in this case. So this can be integrated. So twice, integrate this twice, assuming, because k, we are saying, okay, I should also have mentioned that q dot is being assumed to be a constant. So there is a constant volumetric heat generation throughout the volume. So the solution should be minus q dot by 2k x square plus c1x plus c2. And the solution, because it requires two boundary conditions, so we can always solve it in terms of ts1 and ts2, even though these are not known. But we can apply the boundary conditions that the temperature at x equal to minus L is, let's say, ts1, and temperature at x equal to plus L is ts2. Was there a question? Okay, so using these boundary conditions, you can then obtain that the temperature distribution as a function of x should be q dot L square by 2k 1 minus x square by L square plus ts2 minus ts1 by 2 into x by L plus ts2 plus ts1 by 2. So the temperature profile that I had drawn is essentially a parabolic profile. So the distribution of temperature would be parabolic, and then you can actually differentiate this equation, for instance, to get what would be the point at which the maximum temperature will occur in this problem. Assuming, of course, maximum will happen if q dot is positive. If q dot was negative, if you were somehow consuming, this system was consuming energy, then you will have q dot negative, and so you will actually have a point of minimum temperature. So that is a solution. And then, of course, the other part is that the flux in this case is not independent of the location. So the first derivative of temperature, when you take it, is dependent on x. So flux is not dependent on temperature, and so that is unlike what we have seen in the case of steady state, or in the case of conduction in a plane wall with no heat generation. Now, the reason I chose this x equal to minus L to plus L is for the reason, for this particular thing that I'm going to cover now. Say we look at a scenario where the slab is exposed to a fluid of the same temperature and same heat transfer coefficient on both sides. So what it means is, let's say we have a slab, again of thickness 2L, and this time we have the same conditions on both ends of the slab. So what that would mean is that this temperature distribution would actually now be symmetric, because now we have geometric similarity in the problem. So we'll have a symmetric temperature profile and symmetry about x equal to 0. So the temperatures would be, let's say, Ts on both ends, which we may not know yet, but I will discuss how to get those temperatures. And so we are plotting, I should be more careful here, but we are plotting temperature on the y-axis and Ts on the, so that the temperature on the y-axis and x coordinate on the x-axis. So the temperature profile, as I said, would be symmetric, and if you check the profile that we have, or the function that we just derived, it basically means that ts1 has to be equal to ts2. So you can see that the linear function will actually go away. This function will go to 0, and this will just become ts, because this is the average of ts1 plus ts2, so it will become just ts. So the profile would just be a parabolic, a function which is only a function of x square, which means that it is going to be symmetric, considering that you're going from minus l to plus l, so it's an even function. The second part is that for that kind of a function, or for that kind of a profile, dt dx dt dx at x equal to 0 will be 0. And that is again because of symmetry, that the slope of the function at x equal to 0 should be 0. And that we can also confirm by the numerical solution, or by the solution, if you are not convinced, uh, you know by the idea that that symmetry should give you a slope of 0 at the center. Look at the analytical solution and derive that. You can see that it will actually be 0. So having a 0 slope at a particular point, in this case the center of the plate or the slab, basically means that the problem is the same. This is the same as a problem, or is equivalent to the problem that you may see if we have geometry of this type. So a slab which has a thickness of L only, so x going from 0 to x equal to L, except on one end it is exposed to maybe some conditions, and on the left boundary we have insulation, or the boundary is insulated, so there is no heat transfer across that boundary. So this is an insulated boundary. So the profile again would be the same parabola. So then we get this whole concept of, so the dividing the problem into, plus 2l basically tells me that I don't need to worry about the whole thing. I can even, the solution to the problem is the same as having an insulated boundary on one side, and having the same condition on the other side. So it, at least solutions can be replicated. Of course, the thickness is now only half of the total thickness of the original slab. Now, how do we determine ts? So for this we can use uh, the boundary condition in terms of the flux leaving the slab. So we can say minus k dt dx, god, at x equal to L would be the flux leaving the form of, or would be the convective flux, at the surface. So that becomes h, let's say t s minus t infinity. So then we can differentiate the solution the analytical solution that we have, which would be for the case of the symmetric boundary conditions, and then obtain what would be the value of Ts in terms of T infinity. So you can actually prove, and this I'm skipping now, you can easily say work out that Ts will be T infinity plus Q dot L by H. The same equation can also be worked out by using by not looking at, or rather the solution I would first say, the same solution can be worked out by not worrying about not starting from the differential analysis, but by doing an overall energy balance on this slab. So the overall energy balance approach works quite in quite the same way that we have been using it in other problems. So let's say the slab had some thickness 2L, and we had the center line. So now at some distance, say x, from the center line, I can look at from either end, I should say. So if I look at this section of the slab at some distance x, and I apply energy balance to this section only. So remember, at steady state, energy balance would say that E dot in minus E dot out plus E dot generation should be zero, because this is a steady state problem. So there is no energy coming into this slab or into this section. What we have is energy leaving, and energy is actually leaving in the form of a conduction flux. So we can say minus K dt dx at a distance x into the area, cross section area. And remember, energy is actually leaving from both surfaces. Okay, so I have twice the area, 2 times A. So this should be equal to, so E dot in plus E dot generation is 0. So this should be equal to minus E dot out plus E dot generation is 0. So what is getting generated is Q dot in this thing times the total thickness of the slab, or the total volume, because it's energy generation per unit volume. So let's say 2x into A. So the area cancels in this case. Factor of 2 will anyway cancel. That was bound to cancel because it is the same on either end. So we get the same equation the same differential equation that we actually started off with. So we have minus k dt dx is q dot into x. Now you can see that this is the same as what we had originally when we were trying to solve the differential approach or using differential approach. Okay, so you can integrate this again. The same, basically, we get the same answer all over again, but except this time, of course, this is for the symmetric boundary condition case. So this is based on overall energy balance. We can also apply this overall energy balance over the entire slab to obtain the surface temperature. So if I look at a new control volume, which basically is all the way to the edge of the slab, okay, so this is our control volume, and of course we don't need to worry about the other sections, but anyway, just for the sake of completeness, we can also apply energy balance on this entire control volume. So I can say minus E dot out plus E dot generation should be 0 in this case. So what is E dot generation? This would be Q dot into, let's say, A into 2L. that is the total heat being generated in this volume, minus what is going out, that is in the form of a convective flux. So we have H into 2A, because there are two areas from which heat transfer is taking place, into Ts minus T infinity. So this should be equal to 0. And so we again get Ts to be T infinity plus Q dot L by H, which is basically what I was saying, that we can do even using the flux boundary condition. This is now based on energy balance. So you can use either approach. It depends on what you find to be more suitable. This is some people may find the differential approach to be easier, because there the rules are quite clearly defined, and it works. I mean, the differential approach works everywhere, but this these kinds of energy balances, as I said, this works here because we know that the energy leaving either surfaces is the same, so we can apply symmetry and still be able to obtain the same answer. Now, let's look at heat or thermal conduction in a radial system. So let's look at a cylinder. So in the case of a cylinder, again, we assume, let's say, the thermal conductivity is constant, and Q dot is again a constant. So I'm not going to worry about spatially varying heat generation. We can work out those problems. It's not very difficult, but let's say for the simplest possible case, this is the case, that is the problem that we're trying to work out. This case is slightly interesting, and I'll show you why. Say that we have a cylinder, okay, which has uh, a radius of r naught, and there is uniform heat generation in this case. So Q dot is given. Say the outer surface is at some temperature Ts. Whether Ts is imposed, or it's because of its surrounding fluid, it doesn't matter right now. Okay, but let's say for now that the outer surface is has a constant temperature Ts. So if you look at the governing equation in this case at steady state, we will have 1 by r d by dr of r dt dr. And recall that because I said K is constant, I have pulled out the thermal conductivity from the differential. So plus Q dot by K is 0. Now we can do a little bit of rearrangement and then integrate. So what we will get first is r dt dr minus Q dot by 2K r square plus some C1, and then if I divide the whole equation by r and then integrate again, so I will get temperature T would be minus Q dot by 4K r square plus C1 log r plus C2. So please do verify that it is. Now, what would be the boundary conditions to this case? So the first boundary condition is fairly simple. We know the temperature at r equal to r naught is, let's say, Ts. So that means this should be minus Q dot r naught square by 4K C1 log r naught plus C2. Now we need a second boundary condition. So what do we do? Does anybody have an idea? What should be the second boundary condition for this case? Any idea? Although you have done this actually in fluid mechanics, you have done a problem of this type, which actually was flow, pressure driven flow in a pipe. Do you remember that? So for pressure driven flow in a pipe, you typically get a parabolic velocity profile. But what happened before you got the parabolic profile? Does anybody remember? How do you what should we do with the second boundary condition? No one? Nobody wants to take a shot at least? Okay, I guess nobody wants to. So when you go to the center of the cylinder, what happens to this function? Is this what happens to this function when you go to r equal to 0?
So we need to show that it doesn't go to minus infinity. So like we need to take care of that condition.
Right. So how do we take? So that's a good point. That's what I'm trying to come to now. I'm saying that when r goes to 0, log of r actually goes to negative infinity, right? But we are dealing with a quantity which has to be bounded. You need a mathematically bounded solution. So what should we do at the center then? What should we do at the center?
Should dt by dr be equal to 0 uh, at the center?
Okay, why?
If that's the case, then c1 has to be 0. So even if r tends to infinity or minus infinity, then also the net would be 0. So there will
Well,
be
well,
a
one of
smooth
the things.
profile.
Okay, so let me interject and let me say that r is one coordinate which only goes from 0 to infinity. It doesn't go to minus infinity. Okay, it's not like x, y, and z coordinates. R only goes from 0 to infinity. So the problem that we are facing is definitely at r equal to 0. What should we do at r equal to 0? So you are right that we can take dt dr at r equal to 0 to be 0. Okay, but the logic for that, I will also say, is from symmetry. It may not be very easy to understand what symmetry means here, but you can imagine that you are actually coming from it's a coordinate which is actually you're shrinking the shell, or you're shrinking this thing, and so at r equal to 0 you expect that there has to be some symmetry on either end. So even though r negative is not something which is defined, but you expect that it has to be a profile which just begins from there. It begins with a zero slope from there. What it also does is, when you say dtdr is 0, what it also does is it says that dtdr in this case will actually give you a c1 by r. So if dtdr is 0, that would mean c1 by r has to go to 0, which implies c1 has to be 0. The only way, so the slope has to be actually 0 at that point. The second part, I mean, that is one way of thinking about this. The second way is like the first, I don't know, maybe to the same students who spoke twice, or maybe there was another one who spoke in the first instance. That argument is also right, that this function actually is not mathematically defined at r equal to 0. So the only way the solution can be defined or can be mathematically of any interest is if c1 is 0. So c1 is 0 is the only possibility. That means that now we can calculate c2 based on just one boundary condition, and so you can work that out, and c2 then comes out to be ts plus q dot r naught square by 4k. And so the solution that we will get as a function of r would be q dot r naught square by 4k 1 minus r by r naught square plus ts. And that is actually the same. I'm surprised that you none of you recall that, but when you did fluid mechanics, this is actually the same as a pressure driven flow example. There the independent variable was velocity. You actually had a flow in a pipe where u was a function of r only, and so you get a parabolic profile, and that is what we have actually obtained. There's nothing different. And you did the same thing there again. If you recall, at center at r equal to 0, you would have said that the solution has to be physically bounded, so you take c1 to be 0. So now, similar to the earlier energy balance approach that we have followed, we can also calculate the surface temperature in terms of a heat transfer coefficient. So in case there is a fluid which surrounds this solid, okay, which has some heat transfer coefficient h and temperature T infinity, we can calculate that again. Either we can apply the boundary condition, okay, which would mean that minus k dt dr at r equal to r naught is equal to h, T s minus T infinity, or I could use it in overall energy balance. So overall energy balance would mean that there is nothing coming in from this cylinder, everything is going out. So whatever is going out plus whatever is being generated should be zero. So what is generated is q dot pi r naught square L, assuming it's a cylinder, it's not a sphere, and that should be equal to what is being what is going out. So that is h ts minus T infinity into the area, surface area. So even using that equation, one can obtain Ts in terms of h and T infinity. The last thing I can say is that same approach is also applicable if you are not comfortable with the differential analysis. You can still apply the you can still apply energy conservation and be able to obtain you can still obtain this differential equation that I have written here, which is r dt dr is minus q naught r square by 2k plus c1. You can still obtain this differential equation by using energy balance, by saying that take a shell at a distance r, so whatever is, or take a section at a distance r, so whatever is coming in, that should be because of the heat being generated inside that solid. So same thing that you can do there is sort of like minus k into area, which will be 2 pi rl there at a distance r, into dt dr, that is the heat which is being conducted out of that shell. This should be equal to q dot pi r square L, that is the heat being generated in that shell of radius r. So you get the same differential equation, which is r dt dr is sort of like q dot r square by some numbers, okay, in fact by minus 2k. So same thing can be obtained again, and you can work from there. So there are different ways of solving this problem on these kinds of problems. So what you want to choose is up to you, up to your liking, or up to your comfort level. So I don't want to dictate that choose this method. Both have their own merits and demerits. Okay, so now with whatever time I have left, I will discuss one case now of how whatever analysis we are doing, and an extension of it can actually be easily applied to designing efficient heat exchange devices. Okay, and I will so this will be this is categorized under the heading, especially in your book, it's called heat transfer from extended surfaces. And so to do what we are going to talk about, let me just pull some pictures here. Let me see if I can pull some photographs. Yeah, so let's look at some examples, and then we'll talk about okay, so let's look at these four examples. One I have already discussed in an earlier lecture, but still, let's bring that. Okay, so there are these four devices that you will see very commonly. I mean, one you may not see very commonly because nowadays very few people use desktops or desktop computers. But anyway, one is, as I said earlier, this is the case of heat exchange, or taking away heat from a microprocessor through a heat sink. The second is a car radiator. Okay, so you have heat, you have a cold, you have a rather hot coolant, as we call it. The coolant is brought into a radiator where there's a fan blower which blows air over the outer side, so the coolant is cooled down and then it's sent back to the engine. The third is the case of an air conditioner, where you actually the condensing unit is on the outer side. Okay, so you have these pipes. If I don't know if you how many if you can see this clearly, but let me just extend this to try and show you. So do you have these pipings which are going through where the hot refrigerant is flowing through, okay, and then finally we have this case, which is actually the case of a motorcycle cylinder, a motorcycle engine. So on the on the engine of this motorcycle, you would actually see these kinds of, you know, extensions. So what I'm going to discuss today is, or at least just give you a brief idea before we do more detailed analysis in the next lecture, is first of all, what is common between all these four applications. So if you see carefully, and I hope that you've guessed by now, if you see carefully, what you can notice is that there are these surfaces which extend out from these bodies. So there are these, in the case of a heat sink here, you can see that there are these flat, thin, lines, or these plates which are extending out of the heat exchanger. Okay, the processor is right below it, so it conducts heat into this base of this heat exchanger, okay, or the heat sink, and then heat is actually being conducted through these thin channels, or through these thin extensions towards, in the upward direction. In the second case, if you look at the radiator again, you would notice that there are these pipings which take the coolant through. But then what happens is that you have this fine structure in the radiator, where you have these thin plates, or I can say a thin metallic grid, which basically is there to do some, to help in some way. And that's what we'll discuss in this part. Same thing happens here in the case of an air conditioner. You just don't have tubings, you also have, on top of tubings, you have these, a thin mesh, okay, which goes in, so so that air can actually flow through that mesh. And finally, the case of in cylinder engine cylinder, you have these, here they are more prominent. So you have these structures, right, and air can actually go in and pull out heat. So what is common in all these scenarios is these extensions which are built on maybe a tube, or a base surface. In the case of the cylinder, in the case of the engine and the heat exchanger, you have the extensions built on a surface. So here you have a cylinder, you have the engine, the piston cylinder arrangement, on which they build these extensions. Same thing as I said here already for the heat exchanger case. In the case of a radiator and a window air conditioner, or even a split air conditioner, you actually have tubings, and these extensions are put on a tubing. So we call these extended surfaces are what are called as fins. And their purpose is specifically to enhance heat transfer from, enhance heat transfer between the solid body and the surrounding fluid. So their purpose is to make sure that you can perform a higher rate of heat exchange as compared to what would have been if these were not there. So what is the purpose for doing this? So let's take a very simple case, a theoretical case, that let's say you had a surface which had which is trying to, let's say, exchange heat with some surrounding. So let's say this is a surface which has some area A, and there is a surrounding fluid which has some given conditions. Let's say the surface has some temperature Ts. So the rate of heat transfer between the surface and the surrounding fluid would be given as H A into Ts minus T infinity, which is by Newton's law of cooling. Now, if I want to enhance heat transfer between the surface and the surrounding fluid, there are two options that I have. The first option is that I could increase the heat transfer coefficient H. So I could increase H by maybe having a blower, blow air or whatever fluid it is. It need not be air, but as we'll see, it is more conveniently done for air. So we can have a blower, we can have the blower maybe operate at a higher speed so that you have a higher velocity fluid flowing over the surface. As and we know that fluid velocity increases, h also increases. So we could either increase fluid velocity. The only problem with increasing fluid velocity is that it may not always be possible, because one thing is that to increase the velocity you need to have an external power source. So sometimes an external power source may not be available. The second thing is that h can also be increased to a certain limit. Sometimes you want to have a much higher rate of heat transfer, and the maximum possible increase that you can provide may not be enough to reach the level of heat transfer we require for safe operation of a device. So this may not always be possible. The second option is that we could decrease the temperature of the surrounding fluid. So decrease T infinity. Decreasing T infinity would definitely increase the rate of heat transfer, but this is also a problem, especially when you're dissipating heat to a surrounding fluid whose temperature we do not control. For instance, in the case of a window air conditioner, or in the case of even the motorcycle engine, the surrounding fluid is air. So we don't cool air and bring it into the air conditioner or on the cylinder, or to the surface of the cylinder. It is what it is. So the temperature is something that we cannot control. So even this has its own limitations. The third option that we are trying to now probe in this case of use of fins is that can we increase the area of heat transfer, or increase the area across which energy exchange happens. So increase A. Okay, so the area across which convection heat transfer happens, is it possible? Can we somehow do something to increase this? And that is precisely what fins serve. This is the purpose of these fins, which is to actually increase area by extending a solid into the fluid. Okay, so taking more space in the fluid on the fluid side. So in this case of a flat surface, as I've drawn here, in this case, what we could have is a slightly altered, I would say, reality. We can have maybe, the solid is something like this. So what we can do is, maybe we can extend the solid a little into the fluid side, something like this. So we have this extension now, which is what we are calling as a fin. Now the extension actually provides additional area. So of course there was area which was available originally for heat exchange, but we also have now this area and the area below it and the area on the sides to actually allow heat transfer to happen. So the area is increased, and we will now look at what could be, what is, whether this works always, or what are the limitations associated with this, with these kinds of designs. Ideally, the thermal conductivity of this fin material should be as large as possible for this principle or this concept to work. Now, why do we want the conductivity to be large? As you will see in the next lecture, there is, of course, we have, by increasing the area, we have reduced the resistance to convection, but by adding this extension, we have now created conduction resistance in the problem. Okay, because heat will actually be conducted along the solid as it's also being removed by the fluid. So conduction resistance is incurred, and so we want to minimize conduction resistance by taking a fin of a material which has a high thermal conductivity, so that the resistance can be minimized. In this course we will actually look at different fin configurations, and let me also bring a picture for those fin configurations here. So we will look at some of the following configurations, and this is something that I've taken right from your book. So there are these four configurations that you will commonly look at. So there is a configuration which is called as a rectangular fin. This is a scenario where the fin cross section area remains the same. Okay, so this is a uniform area rectangular fin. The second scenario is also sometimes called as a rectangular fin, but it has a non-uniform cross section area. Notice in this case that the fin cross section is actually reducing as you go from the place where it's attached to the wall to the end of the fin. So the area is actually going to taper down. The third configuration is an annular fin. An annular fin is one in which you have these discs mounted on the cylinder, on the tubing. So you'll have not just one disc, but you'll have multiple discs in the cylinder. And finally, the last configuration is called as a pin fin. So it's like a pin, starting from a solid surface. So this is also a non-uniform cross-sectional problem, even though you can also have a uniform cross-section area. So you have a sort of like a constant diameter tube attached to the surface, but it's in the form of a pin. Okay, so that is the reason it's called as a pin fin. So we look at these some of these configurations in this course. I won't go into every single configuration, and we will also limit, for the purpose of evaluation, we'll limit ourselves to a few designs only. We won't go into every single design because these are hard calculations. These are not simple calculations to do. But anyway, we'll limit it to a certain scenarios only. Okay, so anyway, I'll stop it here. In the next lecture, we will start with an analysis of these fins. We will apply energy conservation to these fins and apply some, derive a governing equation that dictates how heat transfer takes place through these fins. So this is all from my end. Are there any questions about this? Anything?
So the concept behind fins is that like besides increasing the surface area, you're also giving heat another way to go, like to at least go away from the main processor or whatever it is, to at least like go away a bit, and then it can also go away
Yeah.
from
Yes,
convection.
you can think of it this way. Yes.
Okay, sir. Thank you.
As we increase the surface area by adding like multiple fins, so that also ensures that the surface does not get much hotter as like it can melt if the heat transfer rate is quite high just from one point.
No, I don't think that is the right interpretation there. The surface may still fail. In fact, because see, the thing is, it would help. What you're saying will work if whatever you're adding in the form of a fin, let's say whatever material you're adding, if that had an infinite thermal conductivity, right? But because then only, see, the temperature will actually drop along that direction, along the fin. So unless you had an infinite thermal conductivity, in which case you spread out the heat suddenly, I mean, then it makes sense. But then if you have a material which may not be able to spread it at that rate, so the failure may not still be, we cannot go as far as saying that adding an extension to a device will always make sure that it doesn't fail. That I would not say. It may still fail.
Okay, sir.
It depends on the choice of the material. This question actually will be better answered when we look at some calculations. I will show you how where this may actually not be, may go wrong. Just adding a fin may not always mean that you are safe. That we will work out. So we will stop here.